have seen a fundamental theorem of linear inequality, and the consequence of this theorem is that we have some conditions of satisfiability, and we can produce certificates of this satisfiability. Now we want to also continue and show that we can also produce certificates of implications, and that is sufficient and complete. So to get there, we need another concept and another theorem. It's a slightly involved way of getting there, but it's an important concept. Therefore, we are using this route to prove the finally completeness. So we take the route of linear programming. So what is a linear programming? That you have a constraint given like ax less than equal to b, and there is a vector c, and you want to minimize that cx is least amount for ax less than equal to b. So for example, let's suppose a less than equal to b is defined by these constraints, and c is a vector which increases in this direction. Then you want to c of x, you want to minimize. Therefore, you want to go as far away in this direction as possible, and this is the point. So this x will be giving you the minimum value for cx. So we have seen that if you are interested in ax less than equal to b, then somehow y greater than equal to 0 and ya equals to c is an important constraint, right? So that's what we saw in the last theorem. Furthermore, we can it has been observed that this condition holds, right? So if we maximize c of x, a of x less than equal to b, and then minimize yb, y greater than equal to 0 and ya equals to c, then they make equality. We will prove this theorem. This is called LP duality condition. Let's look at an example how to intuitively understand what's going on. Let's suppose we want to maximize c in this direction. Okay, so c is this direction, and so if that is the case, then the maximum value will occur at this corner, right? When that happens, when c can be said in the positive non-negative linear combination of vector a1 and a2, which are the perpendicular of these two lines, and that negative linear combination is stated here. So what is a duality theorem? Duality theorem, then this equality always exists if both the constraints have non-empty solutions. So let's say we will prove this theorem in two parts. First, we will say that the max element will always be the smaller than this thing. So how do we do that? First, we will say, let's suppose ax less than equal to b, and y greater than equal to 0, and ya equals to c. We assume all these things hold, and show that cx is always less than equal to yb. After multiplying x in ya equal to c, we get yax equals to cx. And recall that ax is less than equal to b. So what we can do is since ax is less than equal to b and y is greater than equal to 0, then we can say that yb is greater than equal to cx. So now we know that yb is always greater than equal to cx. If we can show that if we take this constraint and take a conjunction with cx greater than equal to yb, and this is non-empty set, then we can show that the max it meets at an equality. So how do we do that? A set of constraints satisfiable. What do? We turn into a matrix form. For example, ax less than equal to 0 is written like this, and y greater than 0 is written like this. You can check that, and you can see that ya equals to c. You need to translate into A transpose y transpose equal to c transpose, and then you have to break it down into two constraints where you says A transpose y transpose is less than equal to c, and minus A transpose y transpose is less than equal to minus c. Both together implies these constraints, so that's why it produces this and this constraint. So finally, you need to model this guy, and you say c minus c x and bt by t gives you 0. Okay. Then the theorem 13.4 says that if we have this non-negative vectors u, t, v, w, y, which can multiply with this matrix, n equals to 0, that means that this multiplication with this will get equal to 0. If this implication always holds, then we have satisfiability in this constraint. We will show that this is the case. Let's apply this multiplication and get into a simplified form. If we do the multiplication, we obtain this constraint. Now in this constraint, few things to observe, that this t occurs only at this place, and v and w occurs as a like v minus w and v minus w. So what we can do, we get rid of t by saying that this guy is greater than or equal to 0. Okay. And since v minus w are both are non-negative numbers, we can replace them by one number v0, v prime, which has no constraint on it, and that will model the v minus w perfectly. So we simplify our constraint into this form. Now once you have this constraint, we need to say the implication holds always. So what do we do? First assume that lambda is non-zero. If lambda is non-zero, what we can do is we consider this constraint and say lambda dt plus v prime at greater than or equal to 0. The whole game is somehow use this equality in this constraints and obtain this. Okay, so how do we do that? We divide this whole thing with lambda and take a transpose of the whole thing. Now we have a b part sitting here which matches with this ub. Now I can multiply with this whole thing, then I get a ub here. So I multiply with ub and get ua v prime t lambda. Now you can see that this ua, you can apply this equality and turn into lambda c. If I do that, I get the lambda c v prime vt lambda. So this lambda and this lambda gets cancelled, and you get cv prime t. Now since notice that cv prime t, c is a row vector and v prime t is a column vector, and if you put a dot product, it gives you a single value. So if taking a transpose doesn't change anything, so I can take the transpose of this constraint and I find v prime c transpose, which is exactly what we wanted to prove. Therefore this implication always holds. Now we are still left with the case which lambda equals to 0. So how do we handle with lambda equals to 0? Lambda equals to 0 case actually a trivial case, and in that case if we put lambda equals to 0, the left hand side reduced to ua equals to 0 and v prime at greater than equals to 0. And now using these two, we can prove the right hand side. How do we do that? Claim is that ub is greater than equal to 0. Okay, so how do we prove that? Since by assumption you have the ax is less than equal to b is sat, we apply theorem 13.4, which says that if ua equals to 0, then you know that ub equal to 0. So we can just use this theorem and we know that ub is greater than equal to 0. Now since we know v prime c transpose greater than equal to 0, and we know that this guy is sat, therefore what we can say is that you take a transpose of the whole thing is also sat. Now we apply the theorem 13.3, and from that theorem we say that if this guy is sat, then this application must be always true. Since v8 prime greater than equal to 0 is greater than 0, I can conclude v prime ct greater than equal to 0. Therefore their sum should be greater than equal to 0. So therefore my min and max become equal. Now let's look at one more definition, which is called dual space, which means is that max in the Maxwell problem, this constraint is called primal space, and this optimization problem is called dual space. If a dual space of LP problem X is empty, means this set is empty, then the maximum value is unbounded. So let us suppose the dual space is empty. This space is empty. So what do you do? Okay, if this is empty, then due to theorem 13.3, there must be something that AZ gives you greater than or equal to 0 and CZ is less than 0. That was we had proved. Okay. So what you do is, because of that, you can do that. You can always find a z minus z, which we can increase the value of Cx as much as possible, right? So let's suppose you assume that the Ax is less than or equal to b, and then you add simply minus z minus az, let's say greater than or equal to b minus az, and az is greater than or equal to 0, right? So that means this is b, right? So it gives you ax minus z, so less than or equal to b. So therefore x, keep subtracting z on some satisfying assignment keep you satisfied. However, if you see x minus z is greater than or equal to c of x, okay, because cz is negative number. Okay, so you can always keep increasing your value. Okay. So how do we prove the incompleteness theorem? Since ax is less than or equal to b is non-empty and c is a row vector and delta is a number, let us suppose for each x, ax is less than or equal to b and acx less than or equal to delta. If that is the case, then we have the following truth. Okay, so there is a delta prime less than or equal to delta such that cx equals less than or equal to delta prime is a non-negative linear combination of inequalities in ax less than or equal to. How do we prove this? Since the max is bounded, the dual space is non-empty, that we have just proven, and let the max be delta prime. Okay, so max is bounded because cx is less than or equal to delta. Okay. Since both the spaces are non-empty, and we can apply the duality theorem now because both spaces are non-empty, so we can say that ax is less than or equal to b and y greater than or equal to 0 and ax y equals to c, minima and maxima becomes equal. Therefore, there exists a y naught such that y naught b equals to delta prime, y naught a, y naught is greater than or equal to 0, and y naught a equals to c. So because of this, such a y naught exists, we can say that cx less than or equal to delta prime is non-negative linear combination of ax less than or equal to c.